Humans have always been fascinated by the extremes, the biggest and the smallest, the highest and the lowest. The tallest skyscraper and a tiny shack, towering mountains and plunging valleys, massive planets and their tiny moons. We've pushed boundaries at every scale imaginable. And it's not just about numbers, it reflects our deep, relentless desire to understand just how far we can go. In a way, the story of Gulliver and the little people has always been a symbol of something timeless in us. Hello everyone! And even the abstract idea of temperature hasn't escaped our obsession with comparing and measuring extremes. Is there a highest possible temperature? Or could something even colder than absolute zero actually exist? Welcome to our channel. In today's video, we're diving into the hottest temperature ever, and the surprising truth that absolute zero might not be the lowest limit after all. That's right, when it comes to temperature, we can actually go even lower. What is the highest possible temperature? If someone asked you, what's the hottest temperature in the universe, what would you think of first? Maybe the molten heart of a volcano. Sorry, but that's not it. Then, how about the core of the sun? Not a bad guess, but that's still considered pretty mild on the cosmic scale. Inside the Large Hadron Collider in Switzerland, temperatures have reached an astonishing 18 billion degrees Fahrenheit. That happens when protons crash into each other at near light speed. It's hotter than the core of the hottest known stars by a huge margin. And even that isn't the true upper limit. According to calculations, just after the Big Bang, the universe may have reached temperatures of 1.8 trillion degrees Fahrenheit. So, what could be higher than that? Where exactly does the ultimate upper limit lie? And is there even such a thing as a ceiling when it comes to temperature? In everyday thinking, it feels like you can always make something hotter if you just keep adding fuel. But real-world physics doesn't work that simply. As it turns out, there is a limit to how hot things can get. Beyond that, it becomes physically impossible to heat something further. Not even theoretically can you go any hotter. That ultimate boundary is called the Planck temperature, and it's an absolutely mind-blowing 2.55 times 10 to the 32 degrees Fahrenheit. In other words, that's over 255 nonillion degrees, a number so big it's nearly impossible to visualize. At temperatures like that, bizarre and completely unknown phenomena begin to emerge. The laws of physics as we know them simply stop working. According to theoretical models, energy becomes so intense at the Planck temperature that tiny black holes can begin to form. Space itself collapses in on itself. And in the world of physics, even an event that extreme is simply classified as a phase transition. And just like any phase transition, it requires energy to happen. That means the energy gets used to create black holes, and the system can't get any hotter beyond that point. It's a lot like what happens when water turns into steam. If you keep heating water, its temperature keeps rising until it hits the boiling point. But once boiling starts, no matter how much more heat you add, the temperature stops going up. That's because the energy is being absorbed to turn the liquid into gas, so the temperature stays the same. In the same way, once a system hits the Planck temperature, it can't get any hotter. Any extra energy just goes into forming black holes, pushing space and time into a hyper-unstable, overheated state. What is the lowest possible temperature? So we've seen the upper limit. Now let's go in the opposite direction, straight down to the bottom. And what we'll find down there is even more surreal and mind-bending. Here's the spoiler: absolute zero isn't really absolute after all. There might actually be temperatures below it. But that's not even the most shocking part. The real twist is this, and let's build some dramatic tension. The lowest possible temperature can actually be hotter than the highest. Is your brain starting to spin trying to make sense of that? Or are you still holding on okay? Either way, let's keep going. First of all, what exactly do we mean when we talk about absolute zero or 0 Kelvin? That's the same as minus 459.67 degrees Fahrenheit. If you paid attention in science class, you might remember that temperature is a measure of energy. More specifically, it reflects the average kinetic energy of particles moving through space. In other words, it's a statistical average. Inside any given system, there are always some molecules moving fast. They're hot. And some moving slowly. They're cold. But most of them fall somewhere in the middle, not too fast and not too slow. The average of all those motion speeds is what we call the system's temperature. It's kind of like that classic joke about the average body temperature in a hospital. In the ICU, there might be patients with fevers of 104 degrees. Meanwhile, the morgue could be sitting at a chilly 32 degrees. And yet, if you take the average across the whole hospital, you still get a nice, healthy 98.6. So the colder a system gets, the slower its molecules move. At minus 459.67 degrees Fahrenheit, textbooks will tell you that molecules come to a complete stop. But in reality, that's not exactly how it works. And that's where quantum mechanics comes into play. In particular, you've probably heard of Heisenberg's uncertainty principle, the idea that you can't know both a particle's position and momentum with perfect accuracy. Welcome to the world where everything is ruled by chance and probability. If a molecule came to a complete stop, its position would be fully known and its momentum would be zero. But that directly violates the uncertainty principle. So even at absolute zero, molecules still retain what's known as zero-point energy, and the vacuum of space itself continues to tremble with gentle quantum fluctuations. In other words, there's a tiny crack in the ice wall of absolute zero. So, can we use the laws of quantum physics to smash through that wall completely? Believe it or not, yes we can. Let's take a closer look at temperature through the lens of quantum theory. In any system with molecules, energy levels can be thought of like the steps of a staircase. The higher the temperature, the more molecules climb up to the higher steps. As the temperature drops, those molecules move down to lower energy levels, the lower steps on the staircase. That's the key to remember. Lower temperature means more particles settle into lower energy states. When a system hits absolute zero, every molecule has dropped down to the lowest step. There's nowhere lower to go. And the system's entropy, or its disorder, can't decrease any further. So, is that the end of the road? Well, yes, if we're following classical physics. But we already agreed to go all in on quantum rules, didn't we? And quantum behavior loves to break the mold. So what do you do when you're about to lose a game of chess? That's right, you flip the board. And that's exactly what we do with the staircase. We take the bottom step and turn it into the top. There's nothing above that step. So now, the lowest energy state suddenly becomes the highest energy state, a total reversal. Beyond that point, there are no more steps. In physics, a system like this is called an inverted population or a population inversion. And from a thermodynamics perspective, such a system is said to have a negative temperature. Still doesn't quite make sense? Alright, let's break it down even further. In an inverted system, the molecules sitting on the top energy level have nowhere to go but down. And when particles move to lower energy states, that means the temperature is going down, right? So even though we already hit absolute zero, somehow the system starts cooling even more. That's right, this new temperature has actually dropped below absolute zero. The quantum miracle below absolute zero. But the surprises don't end here. In fact, this is only the beginning. In a population inversion system where molecules are stacked at the very top of the energy ladder, something wild happens. It relentlessly transfers energy to any other system with a positive temperature. And I mean any positive temperature. Even if it's 1,000,000,000,000 degrees hot. In other words, this system is technically hotter. Just picture that for a moment. A molecule at absolute zero receives energy from 1 at 1,000,000,000,000 degrees, and in doing so, the first molecule drops into negative temperature, even colder than absolute zero. That's the kind of quantum sleight of hand we're dealing with here. And we're not done yet. These inverted systems still hold even more bizarre and unexpected behavior. For example, as the temperature rises, the energy level actually drops. That's because there are no higher steps left to climb. It's already at the top. And here's the kicker. When energy increases, entropy actually decreases. You might be thinking, wait, doesn't that break the second law of thermodynamics? Not at all. The second law stands firm. It still holds true just as solidly as ever. But let's remind ourselves, what exactly is entropy? It's the measure of disorder in a system. At higher temperatures, molecules move faster and more chaotically, so disorder and entropy goes up. But in an inverted system, adding more energy actually cools it down. And we've already seen why that makes sense. As the temperature drops, particle speed and disorder both decrease, and naturally, entropy goes down with them. It all checks out perfectly. How to flip the energy staircase. Alright, now let's finally tackle the question that's probably been stuck in your head ever since we first brought up this strange system. How do you actually make it happen? In theory or in simulations, flipping the staircase of energy levels is easy enough. But how does it work in the real world? Surprisingly, it's actually possible to do, and not nearly as impossible as it sounds. Okay, maybe not easy, but still way easier than, say, going to the moon. First, you need a molecule with at least two energy levels, a lower ground state and a higher excited state. Then you inject energy into the system using something like an electric discharge, a magnetic field, or a burst of light. That energy causes the molecules to jump from the lower step to the upper one. And just like that, you've created a population inversion, a system with negative temperature. Sound familiar? It should, because this is exactly how lasers work. In a laser, energy is pumped into a special medium in all sorts of ways, exciting the electrons in the molecules and raising them to higher energy levels. Then comes one final kick of energy. The excited electrons drop back down to a more stable, lower energy level, and when they do, they release a photon. That's the light of the laser. Of course, the laser itself, or the medium inside, isn't actually cooled down to a negative temperature. The negative temperature only exists between those two specific energy levels in the molecule. This is a quantum phenomenon happening at an extremely tiny scale. Ulrich Schneider's experiment. In 2013, a German researcher named Ulrich Schneider from the University of Munich successfully created a negative temperature system in a real laboratory experiment. His findings were published in the January 4, 2013 issue of Science, in a paper titled Negative Absolute Temperature for Motional Degrees of Freedom. In the experiment, atoms of potassium-39 were cooled down to just above absolute zero, then neatly arranged into a simulated crystal structure, known as an optical lattice, created using laser light. After that, a magnetic field was applied to push the atoms up into a higher energy state. Now, if the system had been at a positive temperature, the atoms would have repelled each other, making the entire setup unstable. But under the conditions of negative absolute temperature, created by carefully tuning the magnetic field, the atoms actually began to attract one another, making the system more stable instead. And that's exactly what the team observed during the experiment, a clear demonstration of quantum behavior at work. Could an anti-gravity engine become reality? But the researchers didn't stop there. They pushed the boundaries even further. On June 5, 2024, scientists from the University of Cambridge presented groundbreaking results at the annual physics conference held in Fort Worth, Texas. They revealed that when a cloud of potassium-39 atoms is cooled to a state of negative absolute temperature, it reaches a previously unknown quantum phase. In that extreme temperature range, the atoms arrange themselves into a complex and highly structured pattern known as a Kegi Lattice, named after the intricate geometry found in Japanese basket weaving. Quantum gas in this negative temperature state begins to behave in a way that's eerily similar to what we call dark energy, a mysterious force believed to push against gravity and drive the accelerating expansion of the universe. This suggests it might represent an entirely new state of matter. Could this mean humanity is now one step closer to developing a real anti-gravity engine? What do you think? If you enjoyed this video, be sure to give it a thumbs up and share it on social media. It really helps support the channel. Thanks so much for watching. We'll see you again very soon. Take care and goodbye.